So we've done some work really working on with the chain rule in that second equation form directly, which I'll again tend to stress. And what we've really been doing in some of those examples that I've been showing you is this chain rule for powers that they now talk about later in the chapter. All right, so if you have this general form, g of x raised to some power p, all right, we get this chain rule for powers, and that's really what we were just doing in the examples in part 1 on the chain rule, right? That power p comes out front. We really just copy over that inner function. Power is reduced by 1, and then we take the derivative of the inner function. So let's look at a couple examples. Here's example 5, right? Take the derivative of tangent of x plus 10 raised to the 21st power. So this is another good example of this. So let me go to my file here. And so what we want to do is really what we saw in some of these other examples. Right? So when we look at this derivative, right, this is, right, you can see it's really the outer function is something raised to the 21st power, so we'll apply that rule, right? The 21 comes out front. We'll copy over that inner function, tangent of x plus 10. 21 becomes 20, and now then we have to take the derivative of the inner function, which derivative tangent of x plus 10, the derivative tangent will just be the secant squared of x. All right, so that essentially is your derivative for example 5. So if I just go back to the text for a second and show you the solution, maybe a little cleaner than my sketch, but right here that 21 comes out front, copy over the inner function, and 21 becomes 20, and then the derivative tangent of x plus 10, secant squared x. If you really wanted to, you could maybe move the secant squared x out in front here with the 21, but not a big point there. Okay, so example 6 is what I'm going to do next, and this is the composition of 3 functions. All right, so we've got to be a little careful here. All right, really the outer function here is sine of x, sine of something, but now that function isn't just x, it's e, and then to the cosine of x. So it's not just e of x, but cosine of x. So there's really 3 nested functions. The outermost is sine of x. Then the second function is really e the x. And then the innermost function is cosine of x. Those are really the 3 functions we're going to take a look at. All right, so when we look at the derivative here, all right, remember the outer function is sine of x. So our initial derivative, right, the derivative of sine of anything is cosine. But remember, we just evaluate it at that inner function initially. So that's the first step of the derivative, right? Derivative of sine of x is cosine of x. But x is really evaluated at this inner function of e cosine of x. But now we need to take the derivative of the inner function. So your text would show we really have to do derivative with respect to x of e cosine of x. Now remember, really, the outer function here is e to the x, and the inner function is then cosine x. So when we start to look at the overall derivative, all right, it's going to be cosine of e cosine of x. And now the derivative of e cosine of x is, of course, e cosine of x. If you consider the outer function e to the x would be e to the x, but evaluate a cosine of x. But really, e to the cosine of x is just e to the cosine of x. But then we have to take the derivative of cosine of x. And then that would be minus sine of x. Now, we'll just rearrange some of these terms. These terms can be multipliers out front. All right, so you'll see the final answer will be written like this. It'll be minus sine of x e cosine of x times the cosine of e cosine of x. And that would be our final answer. All right, so this is when we deal with, say, 3 composite functions. Again, you got to be a little careful about the logic, or sort of progress through it from sort of the outermost function to the innermost functions. So let me go back to the e-text and again show you their solution. Okay, So the inner function of sine, right? Sine of x is the outer function. The inner function is e cosine of x, but that is also a composite function where the outer function is e to the x and the inner function is cosine of x. So when you look at the derivative, right, the derivative of sine of anything is cosine of anything. So derivative of sine of e cosine of the x is cosine, evaluate that inner function. But now we need to take the derivative of this inner function, e cosine of x. So derivative of e cosine of x is originally just itself, right? E to the x, evaluate cosine of x. And then there's the derivative of that third function, the inner function here, cosine of x, which is minus sine of x. So really this is the first piece, and then the second piece, and then finally the third. And then we'll see these two terms will be moved out front. All right, and there's your final answer. What I like to do is just step through example 7. It's a little more complicated example, but it's just good to see how the product rule can work in conjunction with the chain rule. And this is what they talk about combining rules. So if you look, if we take the derivative of x squared times the square root of x squared plus 1, there's really two distinct functions here, right? X squared is one, and then square root of x squared plus 1 is the other. So we would have to use the product rule here, right? Take the derivative of this times this, and then add, then of course, this times the derivative of this function. So let me just step through the solution. All right, so the product rule, right, we'll take the derivative of x squared, that would be 2x, then times square root of x squared plus 1. And then we switch it up, right? Now we take the first function, x squared, and then the derivative square root of x squared plus 1, right? And there's that derivative there, 1 over 2 times the square root of x squared plus 1. But the piece I want to show you is by the chain rule. Remember, there's an inner function here, right? The outer function here is really square root of x. The inner function is x squared plus 1. So if you see this 2x here, that's really due to the chain rule when we take the derivative of square root of x squared plus 1. Now these 2's will cancel, and x times x squared is x cubed on this term. And they don't show it, but the way you really simplify this is you have to put everything over the denominator as square root of x squared plus 1. So we would multiply this term top and bottom by square root of x squared plus 1. Now any radical term by itself will equal what we have here. So what you really get in this first term would be 2x times just x squared plus 1. That would give you a 2x cubed plus 2x, right? And then 2x cubed plus this x cubed, and then the 2x, they combine it. All right, so I know I'm not showing you those steps, but that's how they would get to this simplified form. Again, just for this example, pay close attention how even in a derivative like this, we have this extra piece now with the chain rule.